In today's video, we are looking at linear alkanes, and in particular, we are looking at their molecular geometry. Now, we've already gone over some aspects of molecular geometry. We've looked at orbitals that have helped us understand bond lengths and bond angles. So bond lengths, for example, we know that a carbon-carbon single bond is longer than carbon-carbon double bond, which is longer than a carbon-carbon triple bond. We've also looked at bond angles, and this is where we used our MO theory, molecular orbital theory, to look at things like hybridization and to see that for, let's say, methane, we know that this angle between the CH bond, the HCH angle there, is around 109.5. Now, one of the things we haven't talked about yet is these dihedral angles, and it's the spatial relationship between a bond and the atoms. So let me show you what I'm talking about. All right, so here we have just a single bond, and as you can see, we can rotate this bond. Now, look at the blue and the white atoms. As of right now, their dihedral angle is 0. I have two pieces of paper here showing the plane between the bond and the atom there. Notice that the planes line up. Here I'm going to rotate 90 degrees. See how the plane that's white is now 90 degrees rotated. This is now 0. 90 degrees rotated to the right. So our dihedral angle here is 90 degrees. This is indicated by the two planes that I have with those pieces of paper. Now, if I rotate another 90 degrees, I have a 180 degree dihedral angle. Notice that the blue atom and the white atom are opposite of each other in this conformation. Let's go back to 0. Okay, blue and white atom on top. Dihedral angle is 0. Rotate 90 degrees. Now we have a dihedral angle of 90. Rotate another 90, and we have a 180 degree dihedral angle. So if we were to take just ethane, for example, so we've got carbon, carbon, and then we have 3 hydrogens off of each of the carbons. We're going to draw this in what's called a staggered form. And what we're going to focus on is H1 and H5 and this relationship. H1 and H5 would be considered to have a dihedral angle of 180 degrees. This is because they're completely opposite of each other. Now, if we look at how we can form this, we're simply just rotating one of the ends of our ethane. Let's look then at the eclipsed form. The eclipsed form here has this H1 and H5 lined up together, similar to how we looked at our blue and our white atoms. They're either 180 or 0. Now, these are just two extreme conformations, and we're simply looking at 2 of the hydrogens, but we can describe these conformations and essentially how these bonds are rotated, and we can look at the relative stabilities and how likely ethane is to be either staggered or eclipsed. Let's draw what's called a Newman projection, and this is a way that we can visually see it on a 2D piece of paper. Notice here I'm using my model kit, and this is a great time for you to open up your model kit and try to build one of these. It would be useful to have it around as you start to rotate these to understand these conformations. Now, we're going to take our model kit and then draw something on our 2D piece of paper that specifies what's happening in the 3D world. This is called a Newman projection, and Newman is actually from The Ohio State University, which is where I got my master's degree from. And so the building that we worked in was the Newman and Wolfram Laboratory. First, let's just redraw this and practice drawing ethane in this staggered form. So this first hydrogen here is in the plane of the paper. So I'm just going to draw a straight line. And then this H5 is also in the plane of the paper. Now for C1, I'm going to label these so that you can see that they match. I have a hydrogen coming towards us, and then I have a hydrogen going back. Okay, and then C2 is the same. Both of these are going down though. So now we have our staggered form drawn with our wedges and dashes. So the way we're going to do this on a 2D piece of paper is we're going to look down this carbon-carbon bond. Let me just show you. So I'm just going to draw an eyeball. It is purple. Okay, we've got a purple eyeball, and this is looking at the C2 carbon, and right behind the C2 carbon would then be C1. When we draw our Newman projection, we simply start with the circle. And in the dot here, this is our C2. Right here, this red dot is our C2. Our C2 has a hydrogen coming straight up. I'll label this with an H1. Right behind this C2 is our C1. And it's hard to see on this piece of paper, but we know that C1 is bound to H5. When you are drawing these pieces and it's behind, if it's on the carbon that's behind this front carbon, notice how it doesn't cross this circle. Okay, let's finish filling in C2. I'll put a 2 right there so we know where we're at. Now we know there are 2 more hydrogens here. We have this hydrogen and this hydrogen. And if we label them based on this, we've got H1, H2, and then H3 is back there. Cool. So the way that I'm going to rotate this is I'm going to have H2 here and H3 will be on the left side. Right behind this carbon 2 is carbon 1. We've already drawn H5 going down. So we've got 2 more hydrogens here. We already drew H5. Now we're going to draw H6, which is coming forward here. And H6 will then be on the right. H6 is wedged. H2 is wedged, and they are on the same side. All right. And what's hiding back here? This is H4, okay? H4 is right here. H4. So H4 is dashed, H3 is dashed, and H4 and H3 are on the same side. Notice how this is mapping onto what we're looking at. We don't see carbon 1, it's behind. It's behind this carbon 2. A Newman projection uses this little circle to identify that the 3 things bound to this center dot is in front, and everything that doesn't cross that circle is actually right behind. It's on that carbon behind it. This is a Newman projection, a staggered Newman projection for ethane. Staggered Newman projections are more stable, and we'll talk about why in just a minute. Let's do an eclipsed Newman projection. So in this case, H1 and H5 are in the same plane. The dihedral angle is 0. Let's again look down this C2. All right, so I'm going to draw my circle for the Newman projection. We can actually go ahead and draw our 3 lines. This middle dot here is our C2. Let's go ahead and label this with red. So here's C2, here's our middle dot, and that is C2. All right, so we have H1 is going straight up. Here's H1. H2 in this blue is coming out towards us. And H3 that's behind is here. Okay, now we're going to go back to C1, which is right behind this red dot. C1 is right behind this red dot. And so when you draw this, you're just going to kind of push the line over a little because you don't want to draw it right on top. You won't be able to see that there's 2 hydrogens there. So you're just going to push it out just a little to the side. This is highlighting, though, that these are right in front of each other. This is about the best way we can do it on a 2D piece of paper. So our H4 is on the same side as H2. It's coming forward. So this side here would be H4. And then H3 and H6 are on the same side. So this line here would correspond to H6. On the previous slide, we drew out our wedge and dash. So let's go ahead and do that as well. There's our H5 and H1. Okay, H2 is coming out forward. H4 is coming out forward. These should be on the same side for our Newman projection. H2 and H4. Cool. And for a dash, we have H6 and H3. And on our Newman projection, we have an H6 and H3 on the same side. Now, these could be switched. It depends on how you take your molecule and flip it over. But remember that if something has a wedge and the other side also has a wedge, it is going to be on the same side of the Newman projection when you're looking right at the Newman projection. One more note about this eclipsed version. You see here that the hydrogens are right on top of each other. This is actually what's called a transition state. Ethane doesn't like to hang out in the eclipsed form. Those hydrogens being right beside each other has an issue with orbital overlap and hyperconjugation, which we'll talk about. So this is a transition state and it's less stable. Transition states are things you can't isolate. They are denoted with this double dagger. All right, let's now look at the energy of this ethane conformation. So we have ethane. As we rotate it, first we're going to start here at 0 degrees is the dihedral angle. And our energy diagram is going to start up high at a transition state. And that's because this is eclipsed. So here's our 0 degrees. Our hydrogens here are right in front of each other in our Newman projection. Now, as we rotate this molecule, the energy of the molecule is going to go down. And so when we hit 60 degrees, we end up getting a staggered conformation. Then as we rotate another 60 degrees, we end up getting another transition state. Now, this is again eclipsed. And this is higher in energy. We're going to rotate another 60 degrees. Then we're going to get another staggered conformation. So our eclipse versions, where they're right on top of each other in the Newman projection, are transition states, and when they're staggered, these are more stable. Let's go over the 2 reasons as to why it's more stable for it to be staggered. One of the reasons is this electron-electron repulsion. Remember how we talked about our orbitals? Well, when you have orbitals that are nearby each other, they don't want to be there. In Vesper theory, we talked about all the orbitals are pushing out as far away as possible, okay? The same thing happens for our molecules here. These hydrogens don't want to be right beside each other. They want to have lots of room. Now, we are not showing the orbitals. You actually don't see any of the orbitals in molecular model kits, right? These are simply just balls and sticks that we put together. But there are those orbitals there, and they don't want to be right beside each other. So here I'm showing that in this case, this is our eclipsed form, where you have this hydrogen and this hydrogen right in the same line with a 0 degrees dihedral angle. These sp3 hybridized orbitals are overlapping and they are unhappy, okay? Now, if we rotate this hydrogen, carbon-carbon hydrogen bond, this dihedral angle we know is 180 degrees. This is going to give us this staggered conformation. Notice here that the sp3 hybridized orbitals are no longer bumping into each other, which makes them happy. Another very important reason is this concept called hyperconjugation. Now, remember about molecular orbital theory. When we have a bonding orbital, we also make a high energy antibonding orbital. So for every sigma CH bond we have using that sp3 hybridized orbital, we also make this antibonding orbital. What I have shown here on the left is a staggered conformation. This blue orbital is this sp3 hybridized orbital, and it's a bonding orbital and it's filled. It has 2 electrons here. The green orbital, green and yellow, is this antibonding orbital. And so here I've drawn the node in this purple dotted line, showing you that this is antibonding. So this is an antibonding orbital, and this is highlighted by saying a sigma star. This is just one way to highlight that this is a higher energy orbital that doesn't have electrons. Now notice that when we're in the staggered form, and I can see this because the hydrogen that I'll highlight here in red, okay, bound to a carbon. All right, and then our carbon-carbon bond, and then here's our carbon-hydrogen bond. Notice it has a 180 degree dihedral angle. This is staggered. And when it's staggered, you can see that there's this overlap between our bonding and antibonding orbital. What happens is there's some interaction. The electrons that are in the bonding orbital are slightly donating into that antibonding orbital. Now, what does this whole thing mean? Well, pretty much anytime you have electrons on your compound, anytime you can spread them out, you're going to lower the energy of your molecule. When we look at the eclipsed form, This orbital overlap between the sigma bonding orbital and the antibonding orbital, it doesn't happen. They aren't lined up in order for that filled orbital that's bonding to donate into that antibonding. One of the key takeaways with hyperconjugation is that anytime you have electrons in your system and you can delocalize them, instead of them being just in one orbital, they can kind of spread out and talk with other orbitals. You're going to lower the energy of your overall system. Okay, so that's kind of the key takeaway with hyperconjugation, which is the second reason why staggered conformations are favored. Let's now look at an energy diagram for all of the different rotations we can do with this conformation of ethane. We're going to start here with an eclipsed form. The hydrogens in the purple and blue, notice how they're right on top of each other. We have a carbon in the front, our carbon in the back. This energy is high. This is a transition state. Now we rotate it 60 degrees to the right. Dihedral angle of 60 degrees between this HCCH bond. And this is at a lower energy, more stable. Staggered is more stable. We rotate again 60 degrees, and what do we have? We have an eclipsed form. I'm just going to write an E for eclipsed. Again, the energy is high, and this is a transition state. There's approximately a 12 kilojoule per mole difference between the staggered and the eclipsed form. If we rotate again 60 degrees, we're going to rotate this over 60 degrees, we're going to have a staggered form, lower in energy. And we keep doing this. Get another eclipsed form, that's a transition state. Rotate 60 degrees again, we end up getting a staggered form. And if we rotate one more 60 degrees over, we end up getting our eclipsed form back, which is another transition state. So as we're looking here, the conformations of ethane go between an eclipsed and a staggered, and we're rotating 60 degrees. The transition states are higher in energy because of the electron-electron repulsion and the hyperconjugation that stabilizes our staggered form. Let's do an example together. We're going to start with butane, which has 4 carbons. We're going to look down the C2-C3 carbon bond. Here's 2 and 3. Now, if we were to redraw this, we know that butane, if I draw it in this form, is going to have 2 hydrogens on each of those carbons. Now, because one of the methyls is coming up, then I draw my wedge and dash down. Okay, and so on this left side, I'm going to draw my wedge and dash pointing up. Okay, this is a nice staggered formation for butane. So we're going to start here. What we're going to do is we're going to rotate this bond here by 60 degrees. I'm not going to draw on the hydrogens. I'm going to simply show you what happens to this methyl. It is now going to be wedged. We're just going to focus on the carbon framework right now. If I rotate another 60 degrees around this carbon-carbon bond, I'm going to have this methyl is still going to be coming forward, but now it's going to be, the conformation is going to be pointing down but wedged. We do another 60 degrees. Now we're going to push it back into the plane. Let's describe these 4 conformations using a Newman projection. Again, we're going to look down this C2-C3 bond. So let's start here. Our first conformation has this methyl going down. Here's our methyl. Okay, and then we have 2 hydrogens coming off of it. The methyl in the back is going up, and we have our 2 hydrogens here. Cool. We have our staggered form. We're going to rotate 60 degrees. Now, the front of the molecule didn't change. We didn't rotate that side of the molecule, so we still have our methyl, our hydrogen, our hydrogen. Notice here that we rotated 60 degrees, so we now have an eclipsed form. Our methyl is over here. We have a hydrogen and a hydrogen. Right, we're going to rotate another 60 degrees. Again, the front of our molecule didn't change. That carbon didn't change. So you can draw it the same. You're just drawing what changed in the Newman projection. By rotating another 60 degrees, we've now formed a staggered conformation again. Cool. Those are favored, lower in energy. We're going to rotate one more 60 degrees. And we're going to get another eclipsed form. These methyls are right beside each other. All right, let's look at these and understand a little more about which one would be favored here. So we know that staggered is favored and eclipsed is not. But in the case of butane, and really any of these alkyl chains that have extra baggage on them, not just hydrogens, we have these methyls. And if these methyls interact with each other, it's going to create more electron or electron repulsion. In our first staggered structure, this would be called an anti-butane. That's because the two methyls are opposite of each other, and it's staggered. Then we have eclipsed. Then we have staggered butane. However, we have this interaction between these two methyls. This is called a Gauche interaction. So this is considered a Gauche conformation, where you have these two methyl groups that are right beside each other. Now, if the two methyl groups are right behind each other, this is a syn conformation. So we have anti, we have Gauche when they're staggered but nearby, and we have syn when they're right behind each other. Anti is favored. These two methyls take up room, and they need to be as far away as possible. If you start to interact in a Gauche manner, this is not making the butane very happy. Now, syn would be the worst. These two methyls are right beside each other. Let's go ahead and rotate this molecule now back to its original anti-butane staggered conformation. So we're going to rotate this one 60 degrees. We're going clockwise again, so our front carbon hasn't changed. Okay. Now we have a staggered conformation, and this is another Gauche interaction. We're going to rotate again 60 degrees. We have another eclipsed form. And it's at this point in time you're starting to realize that your notebook page is looking like a crazy mess of random structures. And it is. That's exactly how you should feel right now. All right, so we have our eclipsed form, and we're going to rotate another 60 degrees, and that's going to get us back to our original anti-butane, the staggered form. Let's go ahead and label these down here. We have eclipsed. And then here we have this Gauche interaction, and this is staggered. Let's draw in our simple line wedge dash drawings for these two structures here. So notice that we've only been rotating this carbon-carbon bond, okay? So we've rotated it again 60 degrees. So that means that only the back carbon here is changing. It's now going to be a dash. And for this last structure, we've rotated yet again. It's going to be dashed to the back here. So the key takeaway is that when you draw these Newman projections, and you're looking at the line, wedge, or dash structure, right? When we're looking at these structures that are simpler, whatever is on the very top or bottom of our Newman projection is just going to be a simple line. If it's on the right side of the Newman projection, the way that I like to rotate it, it will always be a wedge. And then on the left of your Newman projection, this will then be a dash. It's kind of a nice little record-keeping notation that you can think about. Okay, I've labeled all of our Newman projections A through F with orange. And what we're going to do is we're going to analyze the relative energy of these conformations of butane on an energy diagram. Our first Newman projection was an anti-butane, and it was staggered. This was low in energy. So nominally, this is going to be our A. As we rotated this conformation 60 degrees, we ended up getting an eclipsed form, which we know is a transition state, and that's higher in energy. So here's B. As we rotate another 60 degrees, we got a staggered form. However, this is gauche. We had two methyls interacting with each other. So that means that it's going to be higher in energy than our initial staggered form. Notice the gauche that we have here on C. This is going to be higher in energy than our starting A. Okay? Now we're going to move to an eclipse form, and this is where we had those methyls right on top of each other. So this transition state is going to be even higher in energy. So this is our conformation D. We come back down to a staggered conformation, but it still has that gauche interaction. That was E. We're going to have an eclipsed form. That's F. And then we come back down to our lowest butane conformation, which is A. So this is not to scale, but I'm going to give you some relative energies here. So if A was 0 kilojoules per mole, B has an energy of around 15.9 kilojoules per mole. C is about 3.8 kilojoules per mole. D, with that syn methyls right beside each other, not happy. This butane is quite high in energy, 18.8 kilojoules per mole. E has a very similar conformation as C. We see the staggered gauche for C, and E also has a staggered gauche. These have the same energy. The conformations are essentially the same. 3.8 kilojoules per mole. Our conformation for F has the same as B, and this makes sense. Let's go back and look. 15.9 kilojoules per mole. So F here is eclipsed, and B is also eclipsed, and they have the same energy. And so this is the energy diagram for butane. And there you have it. In this video, we talked about dihedral angles, which is really the last piece of us understanding how molecules exist. It's useful for you to understand how to draw Newman projections because we know that these molecules are not 2D. It helps us understand which conformation is lowest in energy and which is highest. When we have those methyls and butane that were right beside each other, that created electron-electron repulsion, which is not good. If the methyls are far enough away, that is where we get a much lower energy conformation of butane. So that's it for our video about Newman projections, and happy drawing, and I'll see you in the next video.